Okay, so I'm going to give you a presentation basically in two parts. First one is effectively just a walk through the steps involved in general image processing for astrophotography. And then I'm going to do a bit of a deep dive into calibration and image signal to noise. I'll explain why I chose to do that. That's going to be a little bit more mathematical, kind of detailed. I'll try to make sure I don't lose people, but we can't cover everything in a 2-hour workshop. So kind of a general overview, and I'm going to talk about calibration, and Rick is going to talk about stretching. These are two topics that we've heard a lot of interest in. And in the case of calibration, sometimes some misinformation out there that I hope to correct, and so that's kind of what we chose to do today. Okay, so the goal of image processing for astrophotography is to try to figure out how do we go from an image like this. This is the Diamond Ring Nebula. It's a planetary nebula. This is just a raw frame, and you can see that it's got a lot of imperfections in it. We've got darkening in the corner. There's lots of modeling. There's a lot of dust and imperfections, and we want to be able to go from that to something like this, which is a final image in color. Star colors are faithfully represented, cropped a little bit, okay? But so we want to be able to figure out what are the steps in going from a low quality image, like a single frame image, to something that has good spatial resolution, detection of faint detail. I emphasize a lot the dark point. I like to be able to pull out the really, really, really dark nebulosity, the stuff that's right down at the very black point. So that's the reason why I'm going to focus a lot on signal to noise, because that's really what controls that, and faithful reproduction of star color. But there's a lot of challenges in terms of imperfections and noise. We've got imperfections in the optical system, like intensity variations across the field or vignetting, dust, scratches. Our optical sensors are not perfect. Our acquisition is not perfect. Satellites, airplanes, clouds, Elon Musk coming in and throwing all kinds of crap up into the sky. Noise due to the nature of the universe. One of the big issues in noise is so-called shot noise, which is just fundamental. It comes from the fact that charge and photons, our unit of light, are quantized. They come in discrete packets, and that actually dominates the noise, ultimately, of our images. So I'm going to quickly just kind of walk through the steps of starting from calibration, which then I'll talk about in more detail later, outlier rejection, debayering. If we have a color camera, a so-called OSC, one-shot color camera, alignment, integration. This actually has several steps in it that I'll go through very briefly. I'm not going to talk at all about noise reduction. It was just too much to try to go into that in a short presentation. And then Rick will talk a lot in detail about stretching. So we're kind of covering the very beginning and the very end in detail, and the stuff in between relatively quickly. So this image flow, or the process flow, I'm taking from PixInsight, the so-called WDP, the weighted batch pre-processing, which some of you use, but it should essentially be the same for any software tool that you use. Okay, so here's just an overview of image calibration. We'll go into more detail later. We've got a light frame. Usually we look at these from the top as a grayscale image. I think it's very useful to think about looking at these from a three-dimensional perspective. And you can see, for example, that the thing in the middle, our planetary nebula, is almost invisible. We see lots of things going very high and very low. Those are hot pixels and dark pixels, which you almost don't see by eye when you look at this image frame, but later on they will show up, believe me. You can also see some vignetting, the darkening at the corners. I have a full frame camera, and so that darkening is about 20% at the edge of the frame, which is far higher than the contrast due to my actual object of image, which again, you really can't see in the middle of this. Right? So what do? Well, there's also an offset on this, that it's got some average value of around 200 or so, 250. So we subtract a master dark that corrects and kind of shifts everything in principle down towards zero. It's not showing this, well, I'm sorry, here's the master dark. The master dark is relatively flat. Ideally, all the imperfections, or many of the imperfections in our light frame, like hot pixels and cold pixels, also show up in our master dark, such that when we subtract these two, we end up with something which is quieter to begin with in terms of having less noise. It may not look that way in this three-dimensional representation, but it does, and is referenced to 0. So a true region of our image where there's no light will be 0 in this, once we subtract off the master dark. Correct for the vignetting along the edges and to any other imperfections like dust. We want to divide this by a master flat. So the master flat is simply an image taken with the uniform light source in front of our telescope. It matches the fall off in light intensity along the edges. You can hopefully see some little dark regions which are dust on the sensor. So when we divide our light frame minus master dark by the master flat, we now end up with a calibrated frame that is flat. It may be offset intentionally from 0. I'm not going to go into that in detail, but in our raw image, there is something called the bias, which is the original offset from 0 of the image as we've taken it. Later on in the processing, there is sometimes added on an intentional offset called the pedestal. The intention of adding in the pedestal is to make sure that even these dark pixels are above 0. So, and most of the image processing programs do not want to have any values less than 0. And of course, when you subtract two numbers, each of which has noise, you have the possibility that some of those numbers will be less than 0.
Quick question, Bob.
Yeah.
Will you be able to share this slide deck with us?
Yes, it already was shared.
Yes.
Oh, it is?
Yeah.
We've got a link in the email that went out yesterday.
Oh,
So
very
if you
good.
Go back to the list, we've got a link where you can go download the whole deck of slides.
Yeah.
Okay, very good.
Yep.
Appreciate that. Thank you.
Yep. I made a few very small changes.
Can you go back to that last slide?
Yep.
Just so I understand. The left is the picture you took.
Yep.
The middle is after you put the master dart into, treated the first frame with the
Yep.
master dart,
Yep.
combined them,
Yep.
and now that's the output that you have at this stage.
Yep.
Now you got the master flat, which is the bright one,
Correct.
and the output again is going to be the calibrated frame.
Correct.
Okay.
Yep.
That's
Yep.
helpful because I've always been confused when I heard light frame master dart. I didn't understand what that was.
Yep. Yeah, we'll talk a little bit about, I like to avoid the term master dark because well, actually, master dark is fine, master flat has some issues with it, but,
Cool.
and we'll go into that in more detail. Okay, so in that three-dimensional image, you can see there's a lot of pixels that are very high or very low. And many of those imperfections are a single pixel wide. And so the next step is usually doing what's called in PixInsight, it's called a cosmetic correction, which is a very weird term, but it's essentially an outlier rejection. And so the first step in outlier rejection is essentially to go through those light frames and to say, if I look at each pixel and I compare it with its neighbors, I can generate a standard deviation as a measure of kind of how uniform is the image in general. And if this pixel is more than a certain number of standard deviations away from the average of this little neighborhood, I'll replace that pixel with the average of its neighbors. And if it's within that standard deviation, then it will be unchanged. Okay, so that's the first step. It's looking within each individual frame and only looking at the surrounding neighbors. We'll see there's other forms of outlier rejection as well, but this is the so-called cosmetic correction. There is a little bit of caveat here that I'll simply mention, that if you're doing wide field photography, so here's a photograph of a large Magellanic cloud that I took down in Chile back in October. If I zoom in on this particular image, the stars are only 1 pixel wide, okay? If the stars are only 1 pixel wide, it has no way of knowing, is that actually a star or is that noise, okay? So under most conditions, if you're using a telescope or a C-star, the smallest stars are more than 1 pixel wide, so as long as you're careful, this is fine. But especially if you're doing, say, Milky Way photography in particular, you're almost certainly what is called undersampled, and in that case, you have to be really careful using this, or you'll essentially eliminate perfectly valid stars from your image. For one-shot color cameras, a one-shot color camera is made by taking a monochrome camera and having a set of 4 color filters, 2 greens, 1 red, and 1 blue. This is the so-called Bayer matrix, or a color filter array. So in processing, we have to pull out from, so the image is actually an interleaved set of red, green, and blue pixels that represent the raw color image. So for color image processing, we have to go through a step of separating into effectively 3 different images, one representing red, one representing green, and one representing blue. Now, if you think about it, if we have this color filter in front of this monochrome array, we only know red at certain places, we only know green at certain places, and we only know blue at certain places. And we know them all at different locations, right? We don't know red, green, and blue at the same location. We only know them at the locations where the filter has been. So we have to interpolate to fill in the gaps between those. And we estimate from a knowledge of where we do know red, what do we estimate is the value of red in the regions in between. So in this case, we have a light pixel right here. It's got dark neighbors. We fill in the gaps by putting a color of red of intermediate intensity. Okay, this is an important step, and there are various algorithms that can be used for this. One of the challenges is because stars have a very sharp intensity profile, it can be a little tricky to figure out the best way of estimating the regions in between in order to make sure that when you're done, the star colors don't have weird fringing or other things going on around them. But in any case, this is the so-called debayering process. We separate this into 3 separate color frames. We interpolate the regions in between, and then we essentially stack them on top of one another to make a composite RGB image. I'm not going to talk about color images in any more than that, but this is an important step. And if you forget to do this, you're going to end up with really weird images. Okay. All right, our next step then is the alignment or registration of the images. So again, I'm assuming we're only dealing with deep sky objects. So we have something which is largely black, and we have a bunch of stars. So the way that image registration works is the program will look and it will find the brightest stars in the image, and based on those brightest stars, it will create some polygons. And it tries to match those polygons in one image to the polygons in another image and identify what do I need to do in terms of translation, rotation, or shearing in order to make one image match the other one. So you pick a reference image, and all the other images are then, the program will figure out what does it need to do in terms of, again, rotation or translation or shearing, and that is done through something called an alignment matrix. This is not super important. I can explain this later if people want. If you're using PixInsight or other programs, it rattles all this stuff as it's going through the processing. You can see what the alignment matrix is. But in the end, we end up with a reference image that we started with and a bunch of other images that are now tilted or maybe squashed. They might be compressed. But they are now registered such that the star, which is at maybe the 2nd pixel over and the 3rd pixel down in this image, is now aligned with the one that is 2 pixels over and 3 pixels down in this image and all of the other images. And regions where there's no data are handled a little bit in a complicated way of making them 0, which we can go into later if anybody has any questions. But the important point is the alignment process is based on a small number of the brightest stars within your image. So if you don't have good signal to noise in the image and you don't have many stars, it's going to have a problem doing the registration. The registration for, say, lunar or planetary is based on a completely different set of principles. This is only for deep sky objects. All right, so once we've got all of our images aligned, we now want to actually integrate them. We want to sum them, right? The whole point is a single frame has a very poor signal to noise. Once we've done all these corrections of calibrating and registering them. Now we want to say we want to put all those images together to make one higher quality image. Primarily what we're trying to do is get rid of the random noise that each image individually has. So we talked a little bit about the idea of the so-called cosmetic correction, which looked at each individual image and compared, say, a bright pixel with its neighbors to see how similar is this pixel to its neighbors as one way of doing outlier rejection. The first step, or at least as part of image integration, another form of outlier rejection is used called sigma clipping. So sigma clipping, instead of looking at an individual frame and looking at its neighbors, it looks at an individual pixel in one frame and says, okay, how does that pixel in frame 1 compared with the same pixel in frame 2 and frame 3 and frame 4? And since all the frames have been aligned to be registered, if we have a bright object, it should appear at the same location in every single frame. If we have a bright object that's appearing in one frame but not in the other frames, it's probably not real. And so the sigma clipping is a way now of getting rid of things like satellite trails or hot pixels that show up in one image but not the other, and it replaces them with a clipped version. It doesn't compare them, or it doesn't replace them with neighbors. I'll go into this a little bit detail in just a minute. But once we have this, our next step is to estimate what is the quality of these images. Some images, this bottom one, it's all speckled. This middle one also has a bunch of speckling, even more speckling. Plus it's got this weird satellite trail. So the software will go through and it will analyze what is the quality of this image. This one's nice and smooth. This one's got more noise. This one's got even more noise. So it will assign these a weighting factor. And I just call them 0.5, 0.2, and 0.3. Somehow they have to sum to 1. Right? If you're adding the images, they should sum to 1. But what we do now is we take each of these images and we multiply it by this weighting factor and we add them all up. So sigma here means sum, basically addition. So we add the jth frame multiplied by the jth weighting factor. So this is just adding all these up, taking the image, multiplying it by its weighting factor, adding them all together, and then it's making sure all the weighting factors add up to 1. And that then is our integrated linear image. So as I've shown it here, we would take this image, multiply it by 0.5, add in this image, multiply it by 0.2, add in this image by 0.3, and I've kind of fudged it so that these 3 weighting factors all add up to 1. But that then is our final integrated image. Yes?
So are you saying with the clipping that the satellite trail and the hot pixels are still ending up in the final picture? They're just
Yeah.
being averaged?
I'll show that in more detail in the next slide here. I'll show you a little more detail.
What determines the weighting factor?
I'll show that too.
Okay.
Good question.
Great questions, okay.
Bob,
Yeah,
So how is the reference frame selected? Do we have to select the reference frame?
the reference frame usually will be, you can select the reference frame, right? Usually the software will pick a reference frame based on a statistical analysis of the images and have some way of trying to identify which frame has the highest signal to noise, and it will generally use that as the reference frame. But at least in PixInsight, you select what is the reference frame. All right, so what is sigma clipping? If we imagine having pick one pixel at one particular location, maybe my cursor's moving too fast. Just pick a location in one image. Here, you can see here, I have a satellite that came through. There's 3 frames showing. It may be hard to see, but it's kind of zooming through the image. So if I pick one of these frames, I can see here's it's actually tumbling. You see this little, like it's oscillating in terms of bright, dark, bright, dark, bright, dark as we go along. But I've got a satellite trail which shows up in this image. So what it does is going to measure, say, at each pixel. So let me just pick one pixel right here, okay? And it's going to measure what is the value of the image at at all of the other corresponding frames. So the frame number is our variable here. Most of the frames, it's going to be relatively dark, and it's going to have just some little bit of noise. But this particular frame, it's bright. So in Sigma clipping, what you do is you choose and you say, I want to clip any pixel which is more than, say, 4 standard deviations away from the average. Okay? Standard deviation, of course, is a measure of variation within an image. So I take all these frames at a particular pixel, I measure the value of the pixel in all the frames, determine what's the standard deviation. That tells me how uniform is that pixel across many frames. And if this particular pixel is much brighter, say more than, I arbitrarily picked 4 times the standard deviation, it will clip that pixel so that, and set it to a value equal to 4 times the standard deviation. So it clips. It doesn't say put it to the average of the other frames, it clips it. And then it sets it, say, to that value. The so-called Winsorized Sigma clipping actually is an iterative process where it does this once through the entire image, and then it will go back and it will recalculate everything. The reason for that is if you have one pixel which is like way bright, it'll affect the standard deviation of the entire image in a way that you will miss other bright pixels that are maybe only 3 or 4 or 5 standard deviations away. So by going through this process iteratively, it makes sure that it handles both the outliers that are really far away and outliers like this one that might be a little bit outside of the threshold. Okay, kind of a detail, but in any case, it replaces it with the clipped version. So yes, these pixels which are too bright, if I set a 4 sigma threshold, it would set anything greater than 4 sigma away from the average value to be 4 sigma. Now in this particular case, if I went through this process again and I recalculated the standard deviation, now with this pixel adjusted to a new value, I'll have a new standard deviation. And so that iterative process kind of helps to be sure that things come back to a reasonable value. Okay, I mean, it turns out this is not a big issue because usually when you have these broad outliers, they're often many standard deviations away from the average, so clipping them at 3 or 4 is usually pretty good. Okay, weighting factors. So weighting factor is based on a statistical analysis of the images, and there's lots of ways you can do the weighting, okay? So in PixInsight, for example, you can do what they call the point spread function signal weight. You can estimate the signal to noise ratio. You can choose almost anything as the basis of the weighting factor. At least within PixInsight, this is usually hidden from you in a way that you don't see it very much. But if you go to a tool called the subframe selector, you can see what are all these different measures of image quality that you might use. If you're interested in having an image where the stars are most round or the stars are smallest, you might pick the full width at half maximum of the stars as your measure of quality. If you're interested in round stars, you might pick the eccentricity, that's a deviation from roundness. If you're interested in having the really dark regions be your measure of quality, you might pick the so-called PSF signal weight, or you might pick the noise level of the image. Lots of ways you can choose what is that weighting factor that is used. PixInsight by default uses this one called the PSF signal weight, which is here, as a measure of identifying what is the quality of each image. And then it will basically weight them. I think I lost something here, but okay. In any case, that's how you determine the weighting factor. You can choose that, and the software will identify that for you. Okay, I mentioned the idea about cosmetic correction versus wind-rise signal clipping, I just wanted to again emphasize that there's two independent ways of measuring outlier rejection. The cosmetic correction looks within a single frame at its neighbors, whereas the signal clipping, which is done after image alignment, looks at a given pixel and compares it with all the other frames at that same location after image alignment, so that anything that is real, a star for example, is it a star or is it noise? Well, if it's showing up in repeated frames, then it's going to be real. If it's a hot pixel, it's going to show up in only one frame and not in all the other ones. So the wind-rise signal clipping is better at getting rid of those.
So when you're dealing with something like satellite trail, why would you clip it to something like 4 sigma rather than bring it down to the average of the pixel that
Yeah.
2 adjacent frames?
Yeah, it's a good question. I think it's done more in the question of like statistical validity, like what statistical rationale do you have to make it equal to the average? And so making it equal to the clipped version is a less intrusive method of manipulating the data in such a way that then if you have many frames, in the end that effect will wash out. So it's very effective at getting rid of the ones that are just way too bright, but also not manipulating the data too much that you risk getting rid of things that are real.
So you're saying satellite trails, something like that would generally be much more than 4 sigma of average, typically.
Satellite trail, not so much.
Airplane flights,
Yeah.
Airplanes, yes. You know, I mean, if you look at that image I showed, you know, it's visible, but it's not saturating the detector or anything like that. But also, it's not just 1 pixel wide. So the first method is really looking for individual pixels that are bright, whereas a satellite trail might actually be a few pixels wide, and an airplane certainly would be more than that.
Yep.
For the cosmetic correction, are there really a lot of pixels that will become hot for one individual image that will appear in the dark?
That's a hard question
Oh,
to
that's-
answer,
yeah.
but maybe the answer will come when I talk about calibration, because I'll
Okay.
talk a lot about that. Again, here's just more the quality weighted integration. Again, in PixInsight, in the image integration tool, you can choose which variable or which weighting you are using in order to in order to do that.
So the default is normally.
The default is the so-called PSF signal weight, which is kind of a complicated, kind of a combination that they've come up with of combination of factors. So it's, I can't identify it as it's not like sharpness or pure signal to noise or pure sharp. It's kind of a combination of things that they've come up with a good kind of general estimate of quality. Okay, and Ruth is going to talk about histograms, but I think an important aspect of this is if you ever look at raw images, usually you see black and maybe you see 1 or 2 stars. It's a real challenge for people doing deep sky photography, like with a 35 millimeter camera where you can't stretch the image. You have almost nothing to look at. But the point I want to make is that stars are very much brighter than the things we often care about, which is the nebula or the other kinds of very dim objects in between. So it's really the dynamic range. We want to be able to capture things that are very bright. We don't want our stars to saturate the detector, because if we do that, we'll lose the ability to pull out color. And the stars will appear bloated, they'll appear fat, they won't look right. So the challenge in astrophotography is often signal to noise. We need to be able to capture very large signals while also capturing very dim signals. And if you just look at a straight image, the maximum value on this scale actually is 1 of the image, and you can see that the thing that I'm interested in is actually very, very weak. So Rick will talk about the idea of stretching and manipulating the image. So this is the same object, it's the Pleiades, And looking at a straight so-called linear image, we see just a few of the brightest stars. After it is stretched to enhance the contrast down in the dark regions and compress the contrast in the bright regions, we end up with our final image. Okay? I'm not gonna talk about noise reduction. Okay, so that's what I had prepared, kind of an overview. So I don't know how we want to handle this in terms of questions now. I'm happy to answer questions on this general process now. Alex?
So, for all the steps you covered,
Yeah.
are there any of that software is particularly or relatively bad at, so the user has to pay kind of closer attention?
All of them.
Okay.
I mean, I have my biases. I focus on calibration a lot, all right? In part because I think the most important thing you care about in the image in the end is the signal to noise, okay? That's in the end what you care about. And I feel like if you lose it at the very beginning in the calibration step, you'll never get it back. So that kind of lends to a philosophy of making sure you don't throw away signal to noise at the beginning and then try to recover it downstream by doing weird things like smoothing the data or using BlurX or other tools when maybe you could have made the data higher quality to begin with by doing things. Stretching is I would say the one that there is the most active interest in, because it is in some ways the most complicated one and the one where there's the most opportunity for user input, and Rick will talk about that. It's also the most qualitative one, in the sense that what you look for in a stretched image is very much like user dependent, okay?
I'll talk about that too.
Yeah, I mean, I am a physical scientist. Part of my research is doing image processing. And so I tend to focus on this like data, and I want things to be scientifically justifiable in what I do. So that in some sense means there's not a lot of choices to be made sometimes, but yeah, anyway, I like to look at things that are statistically justifiable.
Is C-Star kind of doing all this under the hood when they live stack and show you an image?
Yes, yep.
I was wondering if the comment you made about which is subject to error, as we were just talking a moment ago, does that also work for planetary and lunar?
I'm sorry, about which part?
Which is the least reliable that you have to pay most attention to?
Sharpening.
Yeah.
Oh, yeah, alignment is tricky, all right? So in a deep sky image, you align based on the position of stars. In a deep sky object, you usually do something called feature-based alignment, where it analyzes the image and it essentially looks for features that are generally represented as corners and tries to match those. That is very tricky, and also is where some user input is used. And is, in fact, I think the major reason why the software tools used for planetary and lunar are distinct from those used for deep sky imaging is really because of the differences in the alignment issues. And also, you don't have to stretch very much with planetary.
So, actually to extend Alex's question, right? How good is PI? I mean, you did say PI does a bad job about, it's not that good, right, on the steps, but picking up default values for each of the steps, how good PI behaves in a normal image, like in an image that is taken with clear skies, on a typical day. How does PI produce results? With default values.
I'm sorry, you're asking me for a quality assessment of what?
Yeah, quality assessment, yeah.
I mean, I feel like PixInsight generally does a very good job, right? the people who have gone into it, I think, have thought a lot about what are the kinds of images that people usually do, so the tools are kind of optimized around that. But still, it's based on like, what is an average image and kind of what they think you are looking for. So in fact, there's another step in PixInsight called local normalization that is often done by default that actually is problematic. And they kind of think that you want to do that by default, so it's inserted into the process flow, when in reality, it may not be justified and may actually make your images worse. So, yeah.
We're talking about PixInsight a lot, and John promised we wouldn't do zero in on PixInsight. But for example, AstroPixel processor, one of the things I love about it that I recommend it to beginners is that for the most part, you can just take the default values and it'll do a really good, run-of-the-mill job. Might not be optimized perfectly, but it does a good job at it. Cyril, same thing. If you just click the buttons, Cyril does an okay job. So,
Yeah, I think in general, most of them do the default are not bad.
Yeah, I think Bob, there's a little bit of misunderstanding of your comment before about like which steps are stronger or weaker. I think your comment was really just every single step, there are strengths and weaknesses, there are compromises because, there is no perfection there. I think it would be worth like a future session, the various, the relative merits and demerits of the different packages. I think PixInsight is one of the thing I like about it. PixInsight is probably the one that is made the most by and for super math nerds who really care about like, we want to be, everything is super duper statistically valid and every tool has a bunch of different steps that do all the different ways that things could change, which makes it a pain in the ass for beginners to use. But, it's got every tool that they make has just a ridiculous amount of math and statistics behind it. And when you're thinking about the types of images you're taking, maybe that's more than you care about for the kind of result you're trying to get. So I think there was just like a little bit of confusion that from like if you're thinking about this from like a pure data perspective, you're a very big data guy. Everything's a compromise. This question is which compromises are you making in what steps of the process?
Yeah, but defaults are not bad.
Yeah.
Right, so. Okay, the next part then, if we're good with that, I'm gonna jump into a kind of a deep dive on calibration. And to me, this is something I spend a ton of time thinking about. Again, because I'm often trying to push that very darkest region. So I'm gonna talk a little bit about signal to noise, and I already talked about the idea that we need high signal noise because the stars are very bright, the nebula are very dim. We want to capture that, but as a scientist, my life revolves around signal to noise. And when you're doing astrophotography, there's not much you can do to change the signal. You've only got so many photons coming in, you've got a telescope that's a certain size, short of buying a bigger telescope, and then you're only gonna get maybe a factor of 2 or 3 or 4, right? So one thing I learned very early on in my scientific career is if you want to improve signal to noise, focus less on making the signal bigger and focus more on getting rid of noise, all right? So it's easy to introduce noise, and in fact, the very process of calibrating an image inherently introduces noise. So we want to talk a little bit about that. In my experience, we have noise coming in, and I'll call noise, I'm going to use a little bit, I'll talk in more detail about this in a minute, but what do I mean by noise? Noise can be things like dust bunnies or vignettic, where when you look at what should be a uniform image, it appears to fluctuate. That's what I'll call spatial noise. It appears within an image. But also if we take multiple images, we're going to get different results. There's noise in everything that we do, all right? And understanding the origin of that and how to control it is a really important part of this. So again, I think of this in terms of spatial noise. So that's things that in a given frame change on a pixel by pixel basis. That includes things from the optics like vignetting and dust bunnies but also is due to imperfections in the sensors and electronics, in which these are kind of generally lumped together into spatial noise, but in particular sensors have something that's generally referred to as fixed pattern noise. Not all the pixels are equal in a camera. Okay? And the second one I'll refer to as temporal noise, and that simply means if we try to get rid of noise by averaging frames, every time we do a measurement, we will get a slightly different result. So repeated measurements of, say, an individual pixel or an image also gives rise to changes. This so-called temporal noise usually follows the laws of counting statistics, and so we generally think of this as being random noise. This is generally kind of non-random noise, and we'll see that has some important implications. So we want to get rid of the noise. Image processing the image calibration tries to improve the quality of the image. It tries to get rid of some of those hot pixels. It tries to compensate for the fact that I have more light coming to the center of the image than the edges. All those things that I do, subtracting off the dark, dividing by a flat, those images have noise. And therefore, I actually increase the random noise of an image during the calibration process. That is completely unavoidable. Calibration increases the random noise of the image. And so if you're trying to make the image better, okay, by getting rid of, say, the vignetting and other things, you'd like to be sure that what you're gaining by getting rid of the spatial imperfections is not being thrown away by increasing the random noise of the image. So that's a little bit what I'm going to talk a little bit about. Okay, so I'm going to breeze over this because I'm running behind in terms of time. But I think it's kind of useful to think about, like, why do we do what we do in calibration? So there is an assumption that when we measure an image with our camera sensor, that is some response due to the astronomical object that we care about, plus some other stuff. The sensor has some response even in the dark, no matter what. So our first step in calibration is to say, well, if this is true, and what we actually care about is the sensor response from our astronomical object of interest, then we simply take our measured image and we subtract off. What is that dark response? And it assumes that things are simply additive, all right? But that's maybe not a bad assumption. And our second assumption is that the sensor response that we measure is actually due to the incident light as a function of x and y, because it's an image, multiplied by something I'll call a transmission function. A transmission function tells me, well, what's the probability that a photon coming that should hit a particular pixel actually does hit that pixel? The things that would impede that would be dust bunnies, scratches, reflections from the lens. Maybe light coming into the slight off angle has a little bit greater reflection loss than light that's coming right in on the normal axis. So there's a dimming of the image off to the edge that's due to the optics of the image. So if this is true, then the incident light intensity from the astronomical object would just be that we just turn this equation around and say, well, if we take our sensor response and divide it by this transmission function, then we get something which is now a better reflection of the actual light intensity that came from our astronomical object of interest. So that's calibration. And this transmission function is something that we measure that using a flat. A flat is just take a uniform light source, shove it up to the front of the telescope, and see what is the intensity variation across the image. If the transmission function was 1, every photon had an equal probability of generating an electrical signal. That resulting sensor signal would just be completely uniform. But it's not. I showed you the image, right? It falls off toward the edges because we lose light in various ways. So basically, this is the justification for the calibration equation, right? So I wanted to show this because I think sometimes people don't necessarily think about why is the calibration equation the calibration equation? Right? So it has some assumptions built into it, but those are generally pretty valid. So this is what we end up as our calibration equation. Okay, so we take our measured image, we subtract from something that we call a dark frame, and in general, we don't measure one dark frame because each dark frame has noise, and so we want to make sure that the dark frames have less noise by averaging a large number of dark frames, and that's what is simply called a master dark. And likewise, the flat frame, that transmission function, we want to average that, so we average a number of flats, and we subtract from that little dark part that I talked about before. Okay, so there's 4 measurements we need to do. We've got our light, we've got our darks, we've got our flat, and we've got a flat dark, which is a dark image taken under the same conditions as our flat. Right? So 2 kinds of darks. These darks are taken under the same conditions as our light frame. These darks are taken under the same conditions as our flat frames. And in each case, we average some modest number of frames in order to get a calibrated frame, and then we simply add up all the calibrated frames with those weighting functions. Okay, yeah, we'll talk about later.
And where does your bias come in?
Okay, the bias. The so-called bias is part of the dark frame. Okay, the dark. I mean, basically, we'll talk about bias. The term bias is very misunderstood, and I'll try to clarify that. Okay, but you'll see that in a minute. A dark frame measured for a certain length of time contains contributions from the so-called bias, that average offset, and possibly additional contributions from some thermal contribution if you have a long exposure. Now, I'll show you a graph of that in a minute and explain specifically what is a bias frame. So that question will be answered. Okay, sources of noise, lots of things. An important part is that time-dependent noise, and in general, noise from random sources decreases like the square root of the number of things that you measure. And in particular, because of the fact that light and charge are quantized, if we measure, for example, the number of photons that we've detected, the uncertainty in that, or the noise in the number of photons measured, will be exactly equal to the square root of the number of photons detected. I can explain that later if you want, but it's not even just how does it scale. If I collect 100 photons in my signal, I will have 10 photons uncertainty due to shot noise. I can predict that exactly. It comes straight out of the laws of random statistics. Okay, so what does noise look like? Here's an average of 200 dark frames. And highly magnified, so you're only looking at a tiny part of the image, but you can see the individual pixels. And in this particular case, our average is 102. That's primarily the so-called bias, that offset. But we've got some variation around that. We've got a standard deviation of about 6. But if you look at this image and say, well, what does your eye pick out? Your eye picks out those bright pixels, right? And it picks out this kind of funky looking guy in the middle, all right, which actually is repeatable. If I look at my image and average many dark frames, I see this kind of thing kind of speckled all through the image, okay, along with these various kind of things. So we've got a nice quiet image. We've got an average and a median that are close to one another, a relatively small standard deviation, but yet there are these pixels that are higher than that, some also lower, but I focus on the ones that are higher, and some things that are not just 1 pixel in size, but actually extend over a larger region, right? And this is the so-called pattern noise. Pattern noise doesn't have to be or fixed pattern noise. This does not have to be a recognizable pattern, right? This discrepancies, these features, will repeat no matter how many times I average. They will never go away. Averaging will not take away these things. So it's so-called fixed pattern noise. So I make a distinction then between random noise, which will average to 0 if I do enough averaging, and fixed pattern noise, which will never go away. And the fixed pattern noise is the really important reason why we do the calibration, and in particular, why we subtract darks from our lights. Because the fixed pattern noise should be the same, and there's no other way of getting rid of it. Okay? So if, instead of looking at the image, another way of looking at noise is to look at a histogram. So if I look at a histogram of that same image, okay, I've got about 180 units, that's my so-called bias, it's the average amount that dark frame is above 0, and I've got a nice narrow standard deviation. This is an actual plot of the data, and you'd say, well, that looks really good, right? But if I plot it a different way, if I plot it logarithmically, what you see is, maybe it's not quite so good, okay? Now, I know most people are used to looking, say, at a logarithmic plot, but the log plot is much better at looking at the outliers. So if I were to take this and say, well, if I were to say, where should 99% of the pixels be if I have a perfect normal distribution with a standard deviation of 5.7, I would predict all the pixels would land in that green region. Okay? About 99% of the pixels lie within that region. But we've got some that are cold, about 0.4% of the image. We've got some that I'm calling hot pixels. That's about 0.02% of the image. And then we've got some that are, I simply call uncomfortably warm. And that's about 0.6%. Now, your eye is really good at picking out the imperfections. Right? You don't have to pixel peep, right? But your eye is really good in a uniform field of low signal to noise at picking out the imperfections. So even though these imperfections are a very small fraction of the total image, you'll notice them, right? And it'll bug you, right? Okay, this is with a cooled camera. This is data taken with a Canon 5D Mark IV, uncooled, high quality 35mm camera, and it shows rather similar features. It shows a pretty narrow distribution. It kind of broadens out here. You see hot pixels, and you see this little lump here, which I actually think is due to cosmic rays hitting, but I'm not completely positive, but you see this kind of lump here. All right, so these cold pixels are usually not problematic. Your eye just sees it as black. The hot pixels are easy to get rid of because they're way far away from the average value, so the statistical things I talked about are really good at ridding those. But it's these uncomfortably warm pixels which are very hard to get rid of. The outlier rejections do not do a good job of rejecting those without risking throwing away valid data, okay? So this turns out to be relatively important. Now, I made the point before about random noise averaging away and fixed pattern noise does not. Another way of looking at that is to take images and say, I can estimate a dark image and say, what is the noise level of the image, and how does that noise level change as I average more and more and more and more dark frames? So that's what I've done here. This is a 6200, a gain of 102. That's so-called optimal gain, and you see it falls off like a rock. And I've said that, well, random noise should decrease like the square root of the number of averages that I do, but fixed pattern noise does not. So if that is kind of a correct model, then I should find that the noise will fit to a function of like a constant divided by the square root of the number of averages plus another constant. And if I do that, you get the black line here. You can see that black line fits very well, which tells me my way of thinking about it is correct. it also tells me how much is the single frame random noise and what's my fixed pattern noise. Now you'll notice that, again, this falls off slowly but doesn't fall to zero. It falls very, very slowly to the fixed pattern noise. But this kind of highlights the idea that when I average my dark frames, the random noise introduced is between this line and the data point. The fixed pattern noise that I'm getting rid of is this little bit. So when I'm averaging my dark frames, if I'm only averaging 3 or 5 or 10 or 20 or even 30, I'm actually adding more random noise than I am taking away in fixed pattern noise, right? So in a sense, I'm making the image worse, except for the fact your eye is really good at picking out pattern noise more so than random noise, okay? But this is kind of the heart of it, of why you really need to average a relatively large number of dark frames in order to make sure you're doing things correctly. A second aspect that we often look at is, what is the effect of changing the sensor gain? So a gain of 102 versus a gain of 250, exactly the same measurement. What do you see? Exactly the same kind of shape. The actual sensor gain in going from a setting of 102 to a setting of 250 is an increase of about a little over a factor of 4. The signal goes up by a factor of 4. But so does the random noise. It goes from 2.5 to 12. The fixed pattern noise goes from 0.28 up to 1.2. The same factor increase. So the take-home message from this, number one, is if you don't average a reasonably large number of dark frames, you introduce more random noise than you take away during the calibration process. The second one is that going to a higher gain, it makes your signal bigger, but it also makes your noise bigger, both your random noise and your fixed pattern noise, by exactly the same amount. So you do nothing for signal to noise by going to a higher gain, and in fact you throw away dynamic range, because now your bright stars are going to be very saturated, right? And when stars are saturated, you lose the color. Everything's white. Red, green, and blue, they're all at max. So stars are white, even if they're not really white. So the point here is going to higher gain does not gain you anything, okay? And in my calculation, my measurements also on a uncooled camera, very similar results. Going on from an 800 ISO to a 1600 or 3200 signal and noise go up by exactly the same amount. So no gain in reality by going to higher ISO. Maybe it makes it easier to see on the screen. Let's see. Yeah, okay. Skip ahead a little bit. Time-wise, I'm kind of almost at an hour. So anyway, this just shows, again, if I look at these particular pixels as a function of the number of frames that I average, how do they change? And again, the important point here is simply that these don't average away. They average to 340 or 130, even this whole region, they simply don't average away. Okay, now, all right, this is the scary part, okay? So, a lot of people aren't gonna like this, okay? But I've thought a ton about, like, okay, this point of calibration introduces spatial, calibration reduces the spatial noise, right? It gets rid of that vignetting, it gets rid of the dust bunnies, but it introduces random noise. I've emphasized that, well, what you really need to do to help with that is to do averaging. Averaging makes the random noise decrease. The question is, you average dark frames, you average light frames, you average dark frames. How many? 50? 100? 1,000? What do you need to do, and why? Right. So I'm going to gloss over this very quickly, except to say that you can go through a relatively straightforward analysis and determine if you have light frames and dark frames and flat darks and flats, and they have some standard deviation of a single frame that you can easily measure, you can go through a relatively straightforward calculation and say, well, how does each one of those contribute to changing the signal to noise? That equation is best represented in terms of noise to signal, which is 1 over the signal to noise for complicated regions. And I'm not going to go into this in detail. I present this and the derivation of this for people who actually want to understand the details, right? And I am a detail-oriented person. Okay, so we can skip that. Okay.
Aw.
But, you know, it comes out of a couple fairly straightforward statistical features of how do you add, you know, what is the noise when you subtract two things or when you divide two things, and that's all I'm showing here. Okay, the take-home message is, if I look at the numbers in that equation, if you believe it's true, and I'll tell you it is true, okay, we can determine what's important and what's not important. So there's 4 terms that come from the noise in the average light frames, the average dark frames, the average flat frames, and the average flat dark frames. Okay? There's 4 terms. There's something in the denominator. The distance, or the value of the average light minus the average dark. That's a relatively small number in a deep sky object. If I have something that's very dim, this denominator is going to be a small number. On the other hand, for my flat frames, it's a big number. It's around 35,000 compared with, say, 300. So this term is about 100 times smaller than this. And what that means is that the noise from the flat frames is about 100 times less than that from the dark frames under relatively, the noise from the flat frames and the flat darks is much less than that from the light frames and the dark frames. So what does that mean? Well, it means you don't really need to take very many flats, and you also don't need to take very many flat darks in order to have good signal to noise. It doesn't matter very much. You don't need to take 100 flats and 100 flat darks. You can take some much smaller number.
Could it also say that you could ignore flat darks
Well, okay,
altogether? Or?
no, you can't. Well, you can't ignore flat darks because the so-called bias, the average value that you are subtracting off, still needs to be subtracted off, or your flats won't work right? But other than that, you can use almost anything to replace it. I'll show an example of that in a minute. But yes, you're on the right thing. In fact, this comes back to your earlier question, what's the difference between a dark frame and a bias frame? All we're really doing is subtracting off that average value. The noise doesn't matter. If we look at what is the average value as a function of exposure time, and we look at what is the noise as a function of exposure time, for any dark frame less than about a second, nothing matters. We have, and this is a really expanded scale. This is 201 and a half, and this is 202. There's no change as a function of exposure time in either the average value or the noise level, as long as we have an exposure of less than 1 second, or maybe even 10 seconds, depending on how picky you are. So when you're doing flats, you're typically using a relatively short exposure. So those so-called flat darks, you can use almost any exposure as long as it's less than 1 second, or maybe less than 10 seconds. That is often referred to as a bias frame, okay? Doesn't have to be really short exposure, anything less than about a second. If we look at the noise and the value, you can see that as we go to longer exposures, there is a thermal signal that comes in. And especially at longer times, that can be significant, and there is significant noise as well that is introduced above the so-called read noise. So in that numerator, when we're subtracting our flats from our lights, we do need to be careful to match the exposure conditions, because all of these properties of the noise and the average value are in fact somewhat dependent on the temperature and the other conditions. But for the flats, it really doesn't matter. Okay? Okay, so that's kind of the take-home message there. One can go through it.
Could I
Yeah.
just make sure I understand?
Yep.
So, you're saying when you're looking at your flats, which are typically on the range of like half a second or less.
No, your flats, yes.
Flats.
Yes.
And then taking dark flats, but that really, you're saying the dark flat exposure time, because it's so short, it doesn't matter if you've got a 100 millisecond flat and a 200 millisecond flat
Exactly.
dark, it doesn't matter.
Exactly. And like I use RGB filters, when I'm doing my flats, my time for red, green, and blue are all different.
Uh-huh.
I don't have to take 3 sets of flats. I
Okay.
can take 1 set of flats at 1/10 of a second
Uh-huh.
and be done.
Am I interpreting this slide, the dark frames versus the bias frames, right? In thinking that if you're using tracked, pictures with longer exposure times, the bias frame, the thermal noise, you're so far out that the thermal noise dominates compared to the bias. So the bias isn't as relevant.
No,
but if
well,
were
you have to
doing-
read, and I know this is hard to see. This is about 5.2, and this is about 7.8. So even at 512 seconds, the read noise is actually still bigger than the thermal noise. Okay? So, now,
Wait, Bob,
Yeah.
isn't it the other way around?
no, 5.2, I mean, so going from 5.2 up to about 8, I have an increase of about 2.5.
Yeah, okay.
I mean,
I gotcha.
things add in quadrature, so there's like square root of some of the
Sure,
squares
yeah.
you have to worry about. But at least with a cooled camera, I'm really never in the condition where I'm really limited by thermal noise. If I looked at a 35 millimeter camera with a, like my Mark IV, a non-cooled sensor, the thermal contribution would be much more important. Okay, I'm almost done. All right, so then if we go back to that noise equation and say, well, the stuff on the right-hand side comes from the flat frames and the flat darks, that's negligible. I can then look and say, well, how many darks should I take if I have a certain number of lights? How many darks should I take in order to be sure that I'm limited by the light frames? That's what I would like. I would like the dark frames to not be adding significantly to the noise. That means I want to be dominated by the light frames. There's some math involved here. Again, I can go through this later if anybody wants to. It's a little bit confusing, but in any case, you can determine how many darks you need in order to be sure that the noise from the darks exceeds that from, that the noise from the dark frames is less than that contributed from the light frames, okay? And again, I'm happy to go through this if anybody wants. You have to invoke the gain of the detector because the, in order to get the so-called shot noise, which is what you want to be limited, you have to convert from a so-called ADU signal, that is what the sensor gives you, to the number of electrons that were actually generated, and that involves reading the gain of the detector from the ZWO or your sensor manufacturer's gain curve. So I'm not going to go into that, but in any case, just to give you an example, here's the Spaghetti Nebula, something I've been working on, this is a really big object, so I've only got part of it in the frame. I've got 35 light frames, I've got a final frame, or really intermediate frame here. If I look just way up in the corner and zoom in and look at my light frame, I can analyze that. I don't care about that. I care about the one row. So this is the same thing, right? There's my final frame, there's one frame. I can look, what is the mean? and what is the standard deviation, and from that data, I can determine how many darks do I need in order to make sure that the noise from the dark is just equal to that from my light frames. And then I say, well, I don't really want them to be equal. I really want the dark noise to be much less. So from this, I can estimate that, well, 15 darks is minimum. I really want to do more like 60 to 100 darks in order that their contribution to the final product is small. Again, I'm sorry, I'm kind of going through that kind of fast, but because of time, I'm just going to stop there. Then my last slide, really, I don't think I need to read that. You've got it in the script, so that I'll happy to answer any questions, and then we can go on to Rick. Yeah.
Real world, I've set up my system. I've done my 70 dark frames. I've done my light frames. I've got some good imaging. I'm having a good night, and I want to move to another object adjacent to the deep sky object I'm looking at. But I rotate my camera slightly. So now I've kind of messed up my relationship between the dust bunnies and the hot pixels. I start over again, or what do I?
Not for darks.
Not for darks.
No, absolutely no, because all the information, all the things you're correcting for in the darks are sensor imperfections.
They're all the sensors.
They're all the
Take away the
Right, the flats you have to.
The
read.
flats I have to read.
Flats, absolutely, yeah.
Should be able to make one dark library at the temperature that you keep forever, right?
Yeah, so that's the other thing,
Essentially, yeah.
is that
Forever's a long time.
Well,
Yeah.
forever's a long time, pixels start to degrade too with the age of the sensors, you'll get new hot pixels here, new banding there.
But maybe annually.
But to that point on the temperature, I'll have a session, it's 3 hours, and I have the temperature taken at one time, and then another time, and then sometimes the system recognizes that and says you have to retake your darks again.
Okay, so I've done a bunch of measurements from my camera at temperatures between 0 and -30. And over that temperature range, there is very little change. As I get close to 0, there's a very small increase in noise, but I think this is where there's a lot of lore out there based on old generation cameras that had a lot of thermal noise. And the thermal noise can be very sensitive, but I showed you that even at 512 seconds, that's 8 minutes, right? Over 8 minutes of frame time, that's really long, and there's really no need to ever do anything longer than about 2 minutes in reality.
Okay.
So, under most conditions, it's just the read noise. And from what I've seen, the read noise is almost completely independent of temperature. It does go up with gain, right? But yeah, I don't think there's really any need to retake darks.
Okay, good.
Yeah.
On your previous slide where you did the math to determine your minimum number of darks.
Yep.
I understand that, right? You had to actually take pictures in order to know the math, right? There's no way you could have calculated that in advance of using your equipment.
Yes, I need to know what is the standard deviation of one dark frame, and this thing in the denominator, light frame ADU. I have to know what am I shooting for, okay? So what am I shooting for? I measure one frame and I say, well, this is the darkest region. If I really want to get the very best black point, the worst case scenario is the darkest region. The darkest region has the worst signal to noise, okay? When in the shot noise limit, the signal to noise is exactly equal to the square root of the number of electrons you detect, okay? So the signal to noise is worse in the darkest region, and so that's what I picked here as just an area between any identifiable stars as the standard deviation and the mean to throw into here, okay? So 414 minus my dark, which was 100. So, but yeah, I just have to know how noisy is my dark? And what I'm assuming here is that the noise in this region is controlled by shot noise. Right? And that's a pretty good assumption. My dark was 100, I'm seeing 400. That increase in 300 is almost all like just background leaking through, but it's actual light. So I have 300, my gain is 4, so I have 75 electrons I detected. The noise is going to be the square root of 75, which is going to be about 7.5, no, about 8, a little over 8. And my dark frames have a noise of 23. Yeah.
On the bottom of that slide, first of all, it says that that's 35 light frames.
Yep.
And it says 15 darks is the minimum. But then it says probably need 60 to 100, and I'm confused.
Okay.
Because now I've got 100 darks against 35 lights.
Yes. Okay. So I measured 35 light frames. Okay. The noise on the light frames is higher than that of my dark frames. Okay. To begin with, each light frame has a higher noise level than my dark. I just kind of walked through a rough estimate. My light frames are going to have a noise of what, 8 electrons, which translates to about 32 units on my analog to digital converter.
What's ADU?
Just the units on the analog to digital converter. It's the number that you get in the when you read in the value. So I measured 35 light frames. Each one of those has some noise. That noise level is higher per frame than my dark frames. So the question is, how many dark frames do I need such that the noise from 35 light frames is the same as the noise from those dark frames? If I'm just looking to make them equal, because my light frames have more noise per frame than my dark frames, it makes sense that I need a smaller number of light frames to make that noise just equal to one another. But in reality,
Sorry.
I don't want them to be equal. I want the noise from the dark frames to be negligible. And the way I make it negligible is to make sure that I'm averaging more than that number by a factor of 4 or 5 or 6 or 8 or 10.
So if I take 35 darks, 35 lights, at the end of the night, I've got to spend 2 times that time
Easily, yeah,
in order to optimize my darks versus lights.
yeah.
So if I spend 3 hours doing my lights, I got to spend 6 hours doing my darks.
That's why those of us with day jobs don't do this anymore.
I just cover it up and let it run over.
That's interesting.
Yeah, what Bob said about the temperature, even if you have an uncooled sensor, it doesn't matter all that much what the temperature is. So you can just take it home and cap it and run it.
And you don't have to take them all at once either. I've, combined different dark frames. You can take 50 one night and set it up later and take 50. You can take your telescope and put it out on the back porch, which I've done before.
But you said,
The library's good for 6 months or a year,
Yeah,
and so you just got this once a year.
yeah,
And then just combine it into a master dark, and then that's what you use.
Yeah.
yeah.
Is that making sense?
I'm confused because we have to do our darks at the same temperature as the lights, but on a good night, the temperature drops a lot.
But your camera sensor is cool,
It's
right?
chill.
I have a DSLR.
Yeah.
Well, that's why people are buying these chilled cameras.
I know.
So hold up a second, because I use a DSLR, and what I do, now it makes the imaging night really long, but it's the best way to match it, is a lot of them, so I've got a 7D Mark II. It has a built-in dark frame subtract. You can then extrapolate that out in a software, but it will take a dark immediately after the light. Now, an 8-minute light becomes a 16-minute total frame,
Right.
but they are perfectly matched.
Mhm.
Because I have done take the camera off of the telescope, put it on my porch, or take the darts while I'm driving back with the windows open or something like
Yeah.
that. And they never quite match up, because as DSLRs, you were talking about the curve where it's pretty much flat from 0 to -30, and then starts climbing at higher
Yeah.
temperatures.
Yeah.
That curve is a lot steeper for DSLRs and a lot
Yes.
more sensitive to ISO.
Yes.
Like, I've seen differences between 10 and 20C that are dramatic.
Oh,
When
easily.
your ISO is around 2000.
Yes, when you actually, one thing that surprised me actually, I didn't, well, it's a little bit visible here, especially with my DLSR, if I'm taking, actually true with my cool camera too, if I'm taking darks and I use a very short exposure, I see the noise level actually goes up, okay? And because what's happening is the camera is actually getting warm, because I'm transferring data so quickly that although the sensor thinks it's -10, it's actually not. And you can sometimes see even on the monitor, the
Oh,
temperature
wow.
is going up. So in fact, there's reason to say, well, maybe I should take a 1-second exposure rather than 100th of a second, or trying to push it really.
Yeah, they do weird things with really short exposures.
Yes.
And then you also have to look for actual physical, so I do IR, so that's a different thing
Yep.
there. But
Yep.
if you have a battery pack that's also getting warm, you'll get a local variance on
Yep.
that corner of the screen where the battery is heating up the chip a little more.
Oh, yeah.
Okay.
If you're really pixel peaking.
Bob, in the interest of time, I
Yeah.
think we ought to
Yes.
transition to Rick.
I agree.
BioBreak? I certainly need one, so.
I will mention, I forgot to press the record button on Zoom. We intended to record this, and I completely blew it. So,
It is what it is.
We might have to do it again.
You weren't gonna watch it
it is,
anyway.
no, I definitely wasn't